Morning, everybody, and happy Friday, Junior. It's Mr. Poley reporting to you guys with our domain and range lesson. Okay, and yes, if you're wondering, it is still morning. I'm recording this before even my first class of the day. Okay, I think there's an old saying, something about a worm and a bird. How does that go again? Oh, yeah, the early bird gets the worm. So I'm the bird right now, getting the worm with these domain and range notes. And I hope you guys enjoy these as much as me. Okay? So remember from our last lessons on intro to functions, function notation, and composition of functions. Okay, a function converts input values into output values, right? It takes your x's and converts them into y's. Your inputs become outputs after going through some function machine. Okay, so since a function is doing this, and there can be unlimited input values, unlimited output values, or there could be a certain number, there could be finite values, or a finite number of values. Okay, so it makes sense that we can talk about the sets of these input values and the sets of these output values. Okay, so this should be a little bit review, but I understand if things are a little rusty or not in the correct place to be remembered at this time. But if you hear the word domain, you need to think x values. Okay, the domain is your x's. It's the set of all the x's. Okay, then the range, on the other hand, is your set. Is this the right way? Oh, you get the idea. It's a set of all the y's. Okay, the range is a set of all your y values or your outputs. Domain are your x's, your inputs. The range are your outputs or your y's. All right, so we're going to start off nice and easy here with exercise 1. We're going to consider the function that has as its inputs the months of the year and its outputs are the days in each month. Okay, so it helps if you know the calendar, how many months are in a year and what those months are. And it also helps if you know how many days are in the months. Okay, so there's an old catchy jingle that goes, 30 days has September, April, June, and November. All the rest have 31, except for what month doesn't have 30 or 31? February. That's right. Okay, so those are all your months and their days. So we're going to convert that into roster form. Okay, this first exercise isn't really, oh yeah, scratch what I just said. It is really, and you don't know really what, but here we go. So write in roster form the set that represents this function's domain. Okay, so I'm going to put a big D here to stand for, that's right, domain. Okay, so I'm listing all my inputs now, which they told us up here was the months of the year. Okay, so our months of the year. I'm going to shorthand this just because it would take a little too long to write out if I was writing the full months. So we have J for January, F for February, March, April, May, June, July, August, September, October, that's where we are now, November, and December. Okay? So you guys, I hope you guys can make these squiggly brackets. They're really quite fun if you get the hang of it. Okay, so this is our domain. There are exactly 12 inputs for this function, okay, because there are 12 months of the year. But now we go to our range, okay, again in roster form. So that's just a fancy way to say a list with the squiggly brackets on the side. Okay, so our range, the set that represents this function's range. Well, if we forgot what this function's range is, look back to the question. Okay, it says its outputs, so outputs are your range. Outputs are the number of days in each month. Okay, so let's start with the big one, or actually, I usually like to go lowest to highest. Okay, so the month with the least number of days is February, and normally there are 28 days. Okay, then we have September has 30 days, as well as April, June, and November from that catchy jingle. Okay, so we have 28, 30, and then all the rest have 31. So our range has exactly 3 values. There are 3 outputs for this given function. Okay, so there's our domain with 12 values in that set, and here's our range with 3 values. All right, not so bad. Just getting used to writing out the domain and range. This is something we will do quite often throughout the year as we dive into this study of different functions. Okay, so exercise 2 says to state the range of the function f of n equals 2n plus 1 if its domain is the set 1, 3, 5. Okay, so normally if this wasn't mentioned, the domain of this function would be unlimited. It would be infinite if we're speaking in math terms. Okay, it would be infinite because what kind of function is this right here? F of n equals 2n plus 1. That's right, it is a linear function. And without this specific domain, that linear function is going to go on forever. Okay, it is a line that does not end. But they're telling us now the domain is very specifically 1, 3, and 5. So I'm going to fill in my domain right here as part of this mapping diagram. But now I have to figure out what is the specific range. Because again, if this specific domain wasn't here and we were working with this whole function, the range would also be infinite. Okay, because that line would never stop. But luckily for us, we do have a finite number of inputs. So we're going to take these inputs, and we see from this mapping diagram, these inputs, all these domain values are converted to the range values by applying this function rule. And what's the function rule? Oh no, I forgot what it is. Oh, good thing it's right there. F of n equals 2n plus 1. So I'm going to evaluate this function, f of n, for each of these input values. Okay? Each of these numbers in the domain is an x value that will give us a specific y value to go in our range. So we take f of 1, and that means we substitute 1 for n. We get 2 plus 1 equals 3. So f of 1, when the input is 1 for this function, the output is 3. So that goes in my range. Then I take f of 3. Same idea. I'm now substituting. I'm now substituting 3 for n. This board is very finicky today. Okay. So then we get 6 plus 1 equals 7. That's the second value in my range. And the last one, we are evaluating f of 5. So again, substitute that 5 in. We get 10 plus 1 equals 11. So 11 is the final value of our limited range. Okay? 3 domain values convert very nicely to 3 range values, all according to this function rule. Okay? So another way to represent domain and range. Here we have roster form, just 2 different lists. Here we have a mapping diagram. Okay? You guys know in math, there's always different ways to represent the same thing. Because I could very easily take these and write them like I did here. But I'm not going to, because I don't need to. Okay? So moving down now. Oh yeah. Now we're getting into a graph. Okay, now we're working with a graph. The function y equals g of x is completely defined by the graph below. Okay, again, we don't know the equation here. We could take some time to figure it out if you guys really want to, but that's not for now. Okay, we'll get to that later. All right, so this is completely defined here. You guys can see that it specifically starts here and ends over here. Okay, this function does not go on forever. It has a specific starting point and an end point. Okay, so in order to come up with the domain and range of this function, it helps to break it down looking at the minimum and maximum of the x values and the minimum and maximum of the y values. Okay, so this first part says to determine the minimum and maximum x values. So we're looking all the way to the left, right? Because remember, your x is right here. This is your x-axis. My arm is currently transformed into the x-axis. So if we're looking for the minimum, we want to see how far to the left does this function go? Okay, starting at our origin here, 1, 2, 3. Okay, the minimum there is -3 because I had to go backwards. So my minimum x is -3. Okay, what about my maximum? How far right does this function go? Well, again, starting at the origin, I want to count over to that very last point. 1, 2, 3, 4, 5, 6. So that's a +6 because I went to the right. So my minimum x is -3 and my maximum x value is +6. Okay, let's do the same thing with the y values. We need our minimum y and our maximum y. Okay, again, now this is my arm is currently the y-axis. I'm looking for the absolute lowest point and the absolute highest point. Okay, so again, starting at the origin, because the origin is where you start. It's where everything begins. Starting there, 1, 2, 3, 4, 5. This is our lowest point. The function does not go any lower than this. And that was a -5 because I had to go down. Okay, now go the reverse. Want to see where that highest point is. 1, 2, 3. Some of you may be tempted to stop here because that's where the top of the curve is. But you'll see over to the right, there's a point that is 1 above that. Okay, it's very important you get the absolute highest point. Otherwise, you're missing these range values over here. Okay, so that was 1, 2, 3, +4 because I went up. Okay, so we now have our min and maximum y and our minimum maximum x. Well, I went reverse, but you guys get the idea. Okay, we're now going to use these to very nicely write what our domain is and what our range is. So watch how I do this here. The set builder notation. This is what this means. Okay, my domain. Okay, then a little colon there to say, okay, the domain is coming next. Get those squiggly brackets. My domain is the set of all x's such that, you guys remember that term? Okay, such that, that's what this bar is. That is not an absolute value this time. Okay, this is just saying all the x's are such that -3 is the lowest, which you can also write as less than or equal to, because it can be equal to that point. Okay, so it's -3 is less than or equal to x, which is less than or equal to 6. Okay, again, our domain is all the x's such that -3 is less than or equal to x, which is less than or equal to 6. So this just means, in different words, that x is all the values between and including -3 and +6. Okay, once you pick out your minimum and maximum, it's very easy to write out what the domain is. Okay, these numbers here just fall into place. Okay, and the range works the same way. So our range now is all the values of y such that, what's our minimum y value? -5 is less than or equal to y, which is less than or equal to 4. Okay, again, that's just a fancy way of writing that y for this function is all the values between and including -5 and 4. Okay, we know from this that these values are included because we have the less than or equal to, not just the less than. Okay, because these are solid dots here, so we know those points are in fact included. Okay, so the domain of this function, the range of this function. Set builder notation. All right, moving on. Okay, here we go, working with another graph. Okay, it says some functions, right at the top. Some functions defined with graphs or equations have domains and ranges that stretch out to infinity. So like something I mentioned on the front page, consider the following exercise in which a standard parabola is graphed. Okay, the function f of x equals x squared minus 2x minus 3 is graphed on this grid below. So which of the following represent its domain and range written in interval notation? All right, so interval notation, these are all in interval notation. Just a little note here. These straight brackets mean that value is included, and the parentheses or the curved brackets mean those values are not included. Okay? So here we go. Let's see, should we list out the min and maximum? Okay? Let's start with our x's. Do we have a minimum x? Do we have a minimum x? Good question, Mr. Poley. Good question indeed. Well, let's see. That all depends on how this graph looks. Okay? A parabola normally will go up and out for forever, or it could go down and out for forever. Okay? And you guys see, I know it's kind of small on here, but there are arrows on the ends of this parabola. I guess they're not even ends because that means they don't end. Okay, there are arrows here, so that means that's going to continue going up and up and up. But it's not just going straight up, it's going to the left and it's going to the right. So what does that mean about our x values? Is there a minimum? Is there a maximum? If they're going out forever, we don't know where it's going to stop. And technically, it's not going to stop. So the minimum x, I'm going to write NA, and the maximum x, I'm also going to write NA. It is not applicable here. Okay, there is no minimum, there is no maximum for our x's. So where is this function going to go? If it continues all the way to the left and all the way to the right for as long as you could possibly imagine, what is that concept that's way out, that's way down there or way out there? What is that concept? Oh, and I see it on the screen behind me. Okay, so that's going out to infinity. All right, it's a sideways figure 8. That means our domain is going all the way to negative infinity, if you can imagine that, and it's going all the way to positive infinity. Okay, so that means right off the bat, we can see that only number 3, choice 3, gives us that option for our domain. Negative infinity to positive infinity. That's the whole domain. All right? But just to verify this here, our range, when we're looking at the y values, we see that there is an absolute minimum here. Okay, starting at the origin, 1, 2, 3, 4. We have to go down to negative 4. And right there. And since this graph goes right through that point, that negative 4 is included. That's why there's a straight bracket there. Okay? But again, similar idea to the domain, this function is going to continue up and up and up for forever, trying to find infinity. So the range goes from negative 4, which is included, to positive infinity, because positive infinity is up. Okay? But very important idea here, the brackets around your infinity symbols always have to be curved. Why? Why can't I include infinity? Well, guys, we're never going to get to infinity. Okay? It's such a far out concept that we can never possibly include it. Okay? We know that's where our function is going to, trying to get to, but it will never be included. So around infinity, you always need those curved brackets, also known as parentheses. Okay? For most functions defined by an algebraic formula like we have here, the domain consists of the set of all real numbers, okay, most likely. And that's given by the concise symbol R. It's like an R with two trunks, maybe. Okay, sometimes, though, there are restrictions placed on the domain. There are restrictions placed on the domain, meaning the x values, depending on its formula, the structure of its equation. Okay, so two basic restrictions are illustrated in these next two exercises. We're going to go through those right now. So this function, f of x equals 2x plus 1, all over x minus 4, has outputs given by this following table. Okay, so we have our x values on the left, our function values or y values on the right. Okay, so evaluate f of 1 and f of 6. This is something we did a couple lessons ago. So f of 1 means my x is 1. When x is 1, I can see my function is negative 1. Okay, we're strictly using the table here. You could go through and evaluate in the equation, but we don't need to because we have a handy-dandy table. Then for f of 6, same idea. Okay, x is 6. So I go down to 6, and I see that when x is 6, my function is 6.5, or my y value is 6.5. Okay? Here's a question, though. Moving right on. Why does this table give us an error at x equals 4? Okay, at x equals 4. Whoa, there's a big old error there. Why is that? Did our calculator just make an error? Did someone that wrote out this table make an error? Or is there actually some kind of error? Well, look at this equation and look at this x value. What happens when we try to evaluate this thing for x equals 4? Well, let's see. I'm glad you guys asked. That was a great question. Okay, so we take f of 4. That means we have to substitute 4 in for our x's. So I have 2 times 4 plus 1 in the numerator on top of that fraction. And then on the bottom, when I substitute in 4, I have 4 minus 4. Uh-oh. 4 minus 4. What does that equal? Well, 2 times 4 plus 1 gives us 9 over 4 minus 4, which is 0. Dividing by 0, we have 0 in our denominator. Is that possible? Okay, many of you guys might be thinking, oh, well, that equals 0. No. Okay, get rid of that. 9 divided by 0 is not 0. What is it? That is undefined. Okay, you can't calculate the value of 9 divided by 0. You know, guys, it is honestly all fun and games until someone divides by 0. So don't try to do that, okay? You will get an error. It is undefined. Why is it undefined, though? Well, what does it mean to actually divide by something? If you're dividing 9 by 0, you're trying to split 9 of something, maybe 9 apples, into 0 groups. But how can you divide anything into 0 groups? If there's 0 groups, there are no groups. So you can't split these 9 apples into groups that don't exist. Okay? Lesson learned here, you can never divide by 0. And that is why there is a big old error for x equals 4. Okay, you can't have 0 in the denominator. Are there any values except x equals 4 that are not in the domain of f then? Are there any other values besides x equals 4 that would make this undefined? Okay, that answer is no. So no other x values will make this function undefined. And that means for every other x value that you could possibly imagine or think of, as far out to negative infinity or positive infinity as you want to go, any x value other than x equals 4 will work for this function. So no other x values will make this function undefined. Okay? So you can kind of think of x equals 4 as an outcast, unfortunately. Okay, x equals 4 is not wanted in this function. Okay. Last one. Which of the following values of x would not be in the domain of the function y equals the square root of x plus 4? Okay, and explain your answer here. So get us started here. I'm going to take each of these values and see what happens when I plug them in. So y equals 0 plus 4. That's our first x value. And I have y equals square root of 5 plus 4. Then I have y equals the square root of negative 3 plus 4. And I have y equals the square root of negative 8. Whoops, negative 8. So you guys, even I just forgot my negative there. It happens. Okay, so let's see what happens when we clean these up. So this first one for x equals 0 gives us the square root of 4, which equals 2. That seems okay, right? This next one, when x equals 5, that gives us y equals the square root of 9, which equals 3. Okay, so far so good there. We have a 2, we have a 3, nothing fishy going on. Next one, when I have x equals negative 3, that gives me y equals the square root of 1. Which the square root of 1 is just 1. Okay, so far so good. We better hope something weird happens with this last one. Otherwise, we're in trouble. All right, so negative 8, when I have x equals negative 8, I get y equals the square root of negative 4. Negative 4 in the square root? Do we know what to do with those yet? Can we take, as far as we know, the square root of a negative number? No. The answer is no. As far as we're concerned at this point in our mathematical journeys, we cannot take the square root of a negative number. Okay? So that, just like up here, for right now, we would say that is undefined. And because that value is undefined, that means x equals negative 8 is not in the domain of this function. Okay, it's not in the domain because it causes the function to be undefined. Okay? And that, for right now, is domain and range. All right? I hope you guys had as much fun as I did following along. I hope if you guys have questions about any of this leading into the homework, you let me know. Okay? Join my office hours, message me on Remind, send me an email, whatever you got to do, guys. You know I'm here for you. All right? Mr. Poley out.